Welcome to the UGC lecture series. This is a E-Pathashala series and we are talking about the subject computer science. The paper we are going to talk about is machine learning, and in this module we are talking about a very important type of machine learning or function of machine learning called classification, in which we are going to concentrate on a type of classification algorithm called nearest neighbor, and we are also going to talk about certain parameters we are going to use to evaluate this classification. So, classification in essence forms the basis of many of the other machine learning algorithms. Now, this is the development team who is responsible for creating this particular module. Now, look at the learning objectives. So, the learning objectives are as follows: to understand lazy and eager classification learning methods, to explain the basics of nearest neighbor methods, this is very important aspect, and to outline the evaluation methods that is necessary for classification. So, some of the keywords that we will be looking at is obviously lazy and early learning, nearest neighbor, and precision recall, very important evaluation metrics. Now, let us look at what do we mean by this eager and lazy classification methods. Let us look at that first. So, what is eager learning? Eager learning means when given a set of training tuples, we will construct a generalization, a model. We remember we had learning models, which is in this case a generalization or a classification model before receiving new tuples to classify. So, please remember what we are talking about is eager learning. Why do we call it eager learning? Because the model is formed before we see the unseen data. Before we see that, we form the model. So, that is why it is called a generalization model. We use this model to classify new data that comes. So, this is there are different algorithms that come under this class. One is classification by decision tree induction, the next is rule based classification, and then we have classification by back propagation, that is using the neural networks. Then we will be looking at support vector machines, and then associative classification. So, these are some of the methods of which come under eager learning. We will be looking at some of them as we go along further in forthcoming modules. Now, let us look at what we mean by lazy learning. This is also called as instance based learning or IBL. So, what this does is it simply stores the training data, some minor pre-processing you may be doing, and wait until you are given a test tuple to classify. That is why it is called lazy learning. It does not do any generalization, any model, it will be lazy. When it sees the new test data, that time it will do the classification. So, that is why it is called lazy learning. It does not eagerly learn a model. So, it takes less time to train, but it takes more time in predicting, because you do not have a model or anything to directly apply. And so, the learning actually is only storing all the training instances, and classification is assigning a target function to a new instance. So, that is what we call as the lazy learning method. Okay. Now, let us go to the typical approaches that you have for instance based learning or IBL as we read. So, one of the important IBL methods are k nearest neighbor approach, where instances are represented as points in the Euclidean space. We represent these points as in the Euclidean space. We do not do any modeling. Okay. So, that is important. And then we have locally weighted regression method, which will construct a local approximation, and then we have case based reasoning, where we use symbolic representation for knowledge based inference. So, all these are called as instance based learning methods, of which we are going to look at the nearest neighbor approach, and then we will talk about k nearest neighbor in detail in the next module. Okay. So, again we will let us look at eager and lazy classification methods. So, what are the differences between the these two methods? The first one is the differences in computation time. So, if you look at this, eager methods will learn more slowly, but will classify quickly, obviously, because for learning it has to form or it has to build a generalization model. So, that is why it will take more time, but then because you have a model, when you give the test instances, it will classify them more faster. Lazy methods learn quickly, okay, but classify very slowly, because learning does not involve building a model, it just is storing the data points or instances and then training instances, and then when you are doing the classification, it is that time that it does processing. So, classification is slow, or prediction of classification is low. Now, that is about the computation time. Now, if you look at the classification approaches, what is the difference in the approaches? Eager methods commit at training time to a global approximation, because what it does, it takes the training instances, assume that the training instances is a good approximation of what you want to do, and so it builds a single global approximation of the training instances. Lazy methods on the other hand search for a larger hypothesis space. We have already looked at this. Hypothesis space is it and then searches for particular hypothesis. So, it tries to find many hypotheses and uses local functions to form their implicit global approximation according to the target function. So, that is why it takes more time also. So, the lazy does not have a single global approximation, it uses different local functions according to the test instances and tries to have their implicit global approximation which suits the target function. So, here we are going towards a test instances. So, now let us look at a general description of the IBL or the instance based learning methods. Learn by simply storing the presented training data. So, here you are not doing any modeling, learn by storing it. Of course, sometimes when you are storing it you do little bit of pre-processing and all that. Now, when a new query instance, what we mean by query instance is the test instance is encountered. What we do is a set of similar related instances is retrieved from the memory from where it has been stored, and that is used to classify the new query instance. So, when I am doing the training, I am just storing the training data. When a new data is encountered, which is called as query instance, a set of similar instances that have been stored are retrieved from memory and used to classify the new query instance. So, it constructs a different approximation to the target function for each distinct query. So, depending upon the query instance, it approximates. So, it constructs a local rather than a global approximation, local in the sense that local to the target function or the query instance. So, every distinct query instance will have a different approximation. So, this is and if you use complex symbolic representations for these instances, the instance itself are done, some pre-processing is done and you are using a symbolic representation for that, then it is called as case based reasoning or CBR. So, what are the advantages and the disadvantages of this instance based methods? We are not looking at eager now, we are looking only at lazy methods, which is the IBL. So, advantages are, it is particularly well suited for problems where the target function is very complex, because you cannot approximate globally. So, that is why, but it can be described by a collection of less complex local functions. So, the approximations. So, that is why the advantage of IBL. The disadvantages are the cost of classifying new instances is high, because every new instance you have to do most of the computation at that time. So, that is why it is more, the cost is high, and typically it will consider all the attributes of the instances. So, it is very sensitive to the curse of dimensionality. We will come to the curse of dimensionality in detail, but we have mentioned it because the larger the dimensionality, the more complex will be the equation that you do for the local approximation. Okay. Now, again we call these instance based method, as you remember, it is a lazy learning method. So, out of that the k nearest neighbor approach, here the instances are represented as points in a Euclidean space, which we have already discussed, and it uses some distance measure. This is an extra information we are giving here, we are going a little more in detail. So, it uses some distance measure in that Euclidean distance measure to discover the k nearest neighbor. What is this k? The number of nearest neighbor we are going to consider in order to classify the new test instance. So, that is the thing. Now, we go to nearest neighbor methods in general. What do we mean by nearest neighbor methods? So, here we have, it is called memory or case based reasoning. It is a supervised method, because what we do is we record the label instances and the feature value vectors. So, we record that. Remember, it is just storing the training instances. So, when we see a new unlabeled instance, that is in the previous case we called it as query instance, it would be called a test instance or an unlabeled instance, you identify the nearest labeled instance. So, you have a number of labeled instances which you have represented in a space. So, you find the nearest labeled instance, identify that and assign the new instance the same label that is the nearest neighbors, and that is how you do this method nearest neighbor. Consistency heuristic, assume that, now here what we are assuming, heuristics that we are assuming is that a property will be the same of the new instance will be the same, unlabeled instance will be the same as of its neighbor. That is the assumption we are making when we are doing this nearest neighbor. Okay. Now, let us take an example of for the nearest neighbor. So, suppose I want to move the arm of a robo, that is the solution I want. So, you record the parameters and the trajectory moment. Okay. You record all the parameters of the robo arm and the trajectory segment. So, that is your label instance. And then the table that could be, it could contain torques, it could contain positions, it could contain velocities, it could contain squared velocities, it could contain velocity products, it could contain accelerations. So, one as a machine learning person, the system, one of the design parameters is what are the attributes you are going to have for every instance of the data point. So, that is very important. In this case, for example, for a robo arm movement, these could be some of the parameters that you could consider. Okay. So, to follow a new path, you have to break the path into segments and find the closest segments in that table. That is what it means is you find a path and you have the path specified by the torques, the positions, the velocities, whatever is in the table, and you find this path, that segment, wherever it is nearest, that you find in the table. So, you find the closest segments in the table and get those torques, interpolate as necessary, so that you get a value. So, this is what we do for nearest neighbor example. Okay. Now, let us the problem here is the big table, that is you have lot of data, lot of parameters. So, that is an issue there. So, first time with the new trajectory, it will be very what do you say, time consuming. So, closest may not be close, that is another problem. What do you mean by closest? How close? So, I have 10 neighbors and I say that one particular neighbor is close, but does that really mean close? That is an issue that we have. And the table is sparse most cases, because you will not have all the space filled, there will be some spaces there, and it depends on how many data points you are considering. So, few entries only, so the sparseness is another problem. So, the solution in practice is, as new trajectory is attempted, you try to fill in more in the table, so that you have better approximations that you can do later. So, after few attempts, what will happen? This will become very close. So, that is how it does. When you start off, it will not be very good, but as you fill in data and the table becomes more and more filled, your attempts will be more successful and you will get close neighbors. This is defining the close. Okay. Now, let us look at another example. That was the moving of a robo arm. So, now let us look at another example, which is credit rating. Okay. This is a simple example of a credit rating. You have a classifier, you want to look at a person and find out whether his credit rating is good or poor. So, the features you are going to consider it is how many number of late payments has that particular person made per year, and what is the particular person's income or expenses. Okay. So, this is the information we are going to use. So, here we have some A, B, C, D, H, and then you have L, that is the late payments per year, and you have the rating is income divided by expenses, which is the ratio. So, you have that, and you have given some training thing, G is good and P is poor. So, this is an example of a table that contains the names of the people, the parameter which is L, which is late payment per year, and a rating or R, which is income divided by expenses. So, if it is greater than 1, that means this income is greater, and you would see that for all ones it is greater. Sometimes if you have number of late payments more and you have 0.8, you have a poor rating, but 5 number of late thing is only 5, but even if it is 0.7 rating, you are giving him a good. So, it is a training instances. Now, what you have in an Euclidean space, you take L and R, those are the two parameters. Now, look at this is a 2-dimensional space because you are using only 2 attributes. Okay, it is a 2-dimensional space because you are using only 2 attributes. So, this has been sort of we have plotted these values, and this A, B, C, D, these are the people. So, you would see that H, D, E, B are all poor, and A, G, F, G are all F, C are all good credit rating. Now, if you look here, you will see that all the poor are nearer and all the good ones are nearer. So, that is why we say that this distance is a good measure to use for this type of classification. So, now you have I and J new people that are coming into the picture with an H there. So, here you want to find out what the credit rating is. So, here what we do is we have a distance measure. Here we have used a square root distance measure. So, square root of L1 minus L2. Now, what we are trying to do is we are trying to find the distance between any 2 points. So, you have H and you want H is given and you want to find out whether I is nearest to H or I is nearest to this part of the thing. So, for that you have a scaled distance square root of this, you take both the parameters and find the square root. So, this is how it is done and you will find out which is to which it is nearer and accordingly you will classify it. Now, the problem here is about the efficient implementation. Finding the nearest neighbor will take off the order of n, compute distance between. Now, the problem is for every unknown query instance, you have to find the distance between that query instance and all the other points, because you do not know when you will get the closest, right. So, you will have to compare the distance next, and then you have very large data sets. What will happen? The number of points to which you have to compare will be very, very large. So, that is not feasible. So, an alternative is to use a binary search method, so that you reduce the order of log n. So, that is another method you can use, a modification. Okay. Now, another efficient implementation for this nearest neighbor is KD trees. Now, what is this KD trees? Divide the instances into sets based on features, okay. And then what you do? You do a binary branching. If it is example is greater than the value, only then you do the distance calculation. So, there will be about to the power of d leaves with d split depending on the number of attributes, and it will be of the order of log n. So, to split cases into sets, what you have to do? There is only one element in the until you reach one element in the set, you stop. So, otherwise pick a feature to split on, you keep on picking features. So, if you have more number of features, you split it. This is somewhat like another method which we will be using later, I am not talking about it now, but this is just to reduce the time complexity. So, what you do is you find average position of two middle objects on that dimension, and then you use that to find out whether this can fit into come near is a neighbor. So, split remaining object based on the average position and keep recursively splitting these subsets till you get as only single instances. So, this is the KD trees, it is a method. For example, here suppose I have R is greater than some value, yes means I will check the L, otherwise I will no means I will check whether L has to be greater than this value. So, like this I will do and I will get a poor n less. So, I do not have to compare with, why am I doing this? I do not have to compare with all the neighbors. So, number distance calculation will decrease and cost of finding the closest will be pairwise minimum successfully. So, order of log n time, this makes a large difference when you are talking about big data sets. So, basically what you are doing, depending upon the parameters, you are splitting the sets such that you have less number of comparisons to make as you go along. So, what are the issues associated with the nearest neighbor? That is the next question we have to ask. As we have already discussed, prediction or classification can be expensive, especially if there are many features. We have only seen 2 features, 3 features like that. If there are more number of features, that is the dimensionality is higher, then the prediction can be even more expensive. So, there are 2 issues to the time complexity. One is large number of instances means every query instance has to be compared with all the other query instances, for which we use the KD tree to reduce it. The other is the number of dimensions in each feature, in each point is very high, the number of features, then also it is going to become a costly affair. So, and what is affected by the classification? If you have feature noise, that is there are some features that does not give you actual values in the input instances, then you have a problem. So, one entry itself can change the prediction. So, then another issue that you have is the definition of the distance metric, that is very important. Okay. There in the previous example we saw, we used normalized square distance. You can have different methods of distance metric, and this affects the classification accuracy. Another problem that you have is how do you combine the features, that is another issue that you have. And so, there are different types of features, different values, range of values. So, and it is also very sensitive to which features you select for doing the classification. Okay, that is another important aspect of any classification. This is the design perspective that you have to do. So, certain features will help you to classify it in a different way, certain other features will help you to classify it in a different way. So, an instance may have hundreds of features, but only some will contribute to the classification. All these are issues that we have to consider when we are designing any classification problem for that matter. Another problem that you have or an issue you have is ambiguous labeling. So, a particular instance may be labeled ambiguously because of training noise, because of other things. So, the solution here is k nearest neighbors. There we considered, now up to this point we have considered the query instance with each and every instance separately. Now, what we are doing is we have the k nearest neighbors. We will be discussing this in detail in the next module. So, instead of using not only a single neighbor, we are going to use k neighbors, k instances to compare with, and there are different methods that we can do. We will discuss this later. Compared to the k nearest neighbors, instead of comparing it to only one neighbor, and the label we will label according to the majority, like a voting principle. Okay. And now the question arises, okay, I am saying I am comparing it with the k neighbors, what should this value of k be? That is another interesting question, it is still a research problem. What is the optimal value of k? As you can guess, it does depend a lot on the characteristics of the data set. Okay. And just to be on the safer side, when we are talking about classification, unless you give your training set to be representative of what classification you want to do, your classification cannot be successful, whatever may be the method you use. Okay. And in the case of k, often 3 is a good. Why is 3 good? We do not know, but 3 seems to be good. We will come to this later again when we are talking about k nearest neighbor. Now, some other issues that we have is, what is a good distance metric? This is a question that already we have discussed. What is a good distance metric? So, how should the features be combined in order to build the good distance measure? So, some strategies that we have here is, you can use a weighted Euclidean distance. What does this mean? Some features will be given more weight than other features. So, that is the weighted distance. And you can also do feature scaling, so that different range of values do not affect the calculation of the distance. So, that is called as normalization, and you can have a good starting point. One way of doing that normalization is mean divided by the feature standard deviation, that is one way of doing that, and it will rescale all the values between the values 0 and 1. So, that this range problem does not come into the picture, but this does not give any particular importance to a particular feature and all that it does not do, but it just does the scaling of the values. Okay. Then another issue is, what are the features we should use, the selection of features that we discussed. So, for example, for credit rating, there are many possible features you could have used. We used what? Number of late payments per year, and we used income divided by expenditure. Okay. But you could have used tax bracket, you could have used debt burden, you could have used retirement savings and so on. So, what features should we use is an important question when we want to do. Then nearest neighbor uses all the instances. Should we use all the instances is another question. So, another thing is, it uses all the instances and it uses all the features of the instances. Is that relevant? There are many irrelevant features that you do not have to consider at all. It does not contribute to the classification. Then why should we consider that? That is another question. So, that is the fundamental problem with nearest neighbor. Okay. So, when do we use nearest neighbor? That is the next question. All the instances that we have, the training instances, should map to points in a space called R. It should map to R. Okay. And there should not be more than 20 attributes per instance. If you have more than 20 attributes associated with each instance, you cannot use nearest neighbor because it becomes too computationally expensive. If you have lots of training data, it is good because it will give an average value. The advantages of nearest neighbor are, it can learn complex target functions because you are doing local approximation for every query instance. There is no loss of information as such. So, these are some of the advantages of using nearest neighbor approach. Next is fast training. You have to just record the feature vector, you can output the value set. Okay. So, there is no question of time required for modeling or training, and you can model any variety of functions. You have complex decision boundaries, weak inductive bias, all this does not come into the picture when you are, if you have done the feature selection properly and if you have done the normalization properly and so on, weighting properly, any model in theory can be handled and it is generally applicable. So, that is the advantage. So, what is the summary about nearest neighbor? The summary is as such, it is a training, the nearest neighbor, training is just recording the input vectors and the output value for that particular input vector, that is called labeling, and prediction is finding the closest training instance to the new data or the unlabeled data or the query instance as we called it. prediction or classification. Efficient implementations are available and fast training very general and it has little bias. The disadvantage is that you need to do some scaling, it is sensitive to noise and you may land up with lot of extraneous features that affect the classification, but are actually not part of the classification. The next part of this module will talk about evaluation. So, we are going to talk about evaluation measures. So, what are the evaluation measures associated with classification? We are only restricting ourselves to classification. So, in this module, first part is about classification and nearest neighbours. There is a particular nearest neighbours which is called KNN or K nearest neighbours, which we will be discussing in detail in the next module. But here we are going to talk about evaluation measures in general about classification. Okay. So, the first one is what is called as predictive accuracy. What is this accuracy? Accuracy is the number of correct classifications divided by the number of total test cases you are giving. Okay. So, that is what is predictive accuracy. Next is efficiency. What is efficiency? Time required to construct the model. Here we did not have a model because we used lazy learning, but in eager learning this time is an important aspect, and the time to use the model, both are important. Time to build the model and time to use the model. This is specifically true for eager learning methods. Then robustness, how can it handle noise and missing values? This is very important in classification because you do not, it is a realistic approach and you cannot ensure that all the labeling will be correct and there is no missing values. Missing values in the sense missing values that contribute to the classification. Scalability is another one, that is you must be able to handle the large data sets. Interpretability is the other, understanding or how is the classification done, understanding or interpreting the model, is the model interpretable. This is again applicable to eager learning and not lazy learning. And then compactness, the size of the tree or the number of rules that you have, these are other issues that we will consider. Accuracy is only one measure and is not suitable for all applications. So, there are some other one in classification, individual highly unbalanced data, that is interesting and also, and we are interested in finding out the minority class only, that is another interesting aspect of classification. High accuracy does not necessarily mean that you have detected things that belong to the minority class. So, that is not necessary. So, for example, 1% intuition achieve 99% accuracy, nothing is gained by those classifications. So, you can you may be interested only in documents of a particular topic, but that particular topic may have only small number of documents. So, that does not mean that the accuracy, high accuracy will give you a good classification for that minority topic. So, that is what we are talking about. And the class of interest is commonly called the positive class and the other class is called the negative class. Now, based on this positive class and negative class, you have some other evaluation measures. So, before we go to those, we will just talk about the evaluation methods. There is one called the holdout method. So, the available data set is labeled with classes and it is divided into two disjoint subsets, and the training data set uses part of this. Again, this is for eager learning. So, you use that labeled data set and learn the model, and then the rest of it, the holdout set as it is called, is used for testing the model. So, this is one method. The training set should not be used in test set, should not be used in learning. This is very important. So, the unseen test set provides a unbiased view or estimate of the accuracy. The next mainly used when D is very large, otherwise you do not have this test set and training set. Now, you have what is called as n-fold cross validation. The available data is partitioned into n equal size disjoint subsets. So, suppose you have 1000, you may classify it into say 200, 200, 200 and 5. So, that means it becomes a 5-fold cross validation, and then use each subset to test and combine the rest of the n minus 1 for the training. So, 1 of the n. So, first 200 and the rest of the 4 200s you will join together, use that for testing, training, and use this one for the test. So, that is one method. The procedure is run n times because every time you will take one of the subsets as the test set, different subset. So, this is, and then you will judge the accuracy by taking the average. So, 10-fold and 5-fold cross validation are typically used, and this method is used when the available data is not too large because you are using the same thing again. Then you have leave one out cross validation, used when the data set is very small. It is a special case of cross validation, and you will each fold of the cross validation has only one single test sample. The rest of it is used in training. So, that is the way. There we used a set, here we used one. So, if the original data has m samples, you will have an m-fold cross validation, because every sample will be left out, trained, tested, left out, trained and tested. Then you have a validation set. Available data is divided into 3 subsets: training data, validation set and a test set, training set, validation set and a test set, and it is used frequently for estimating the parameters in the learning algorithms. And that after that is done, a test data is a separate set which will be used finally for the testing. So, this is another method. So, cross validation we have n-fold, leave out and validation set. It can be used for parameter estimation as well. Now, there are precision and recall measures that are again used for classification, especially in information retrieval and text classification. You use a confusion matrix here. So, you have positive samples and negative samples. So, the actual positive which is classified as positive is called true positive. The actual positive which is classified as negative is called false negative, and the actual negative which is classified as positive is called false positive. The actual negative which is classified by the system as negative is called true negative. So, this is the 4 terms that we are going to use here, and what we do here is, this is what I said, the number of correct classification of the positive samples, which we have already discussed this. Now, precision P is the number of correctly classified positive samples divided by the total number of examples that are classified as positive. So, TP is the number of classified samples, positive classified samples, divided by the total number of positive samples classification, which is TP plus FP. So, that is the definition of precision. And recall R is the number of correctly classified positive examples TP divided by the total number of actual positive examples in the test set, which is nothing but TP plus Fn, that is the total number of positive samples. So, these are 2 measures, precision and recall, in terms of classification. And if you take an example, for example here actual positive is 1, classification negative is 99, and similarly we have given here. So, precision P is as I already discussed, and this is the recall which we have already discussed. So, you will get the confusion matrix gives precision P as 100% and recall as 1%. Only one classified positive example correctly and no negative example has been classified wrongly. Precision measure only recall from the viewpoint of positive class, it does not bother too much about the negative class. There are other evaluation measures also. One is called F measure or F1 score, which is a combination of precision and recall. It is hard to compare 2 classifiers using 2 measures. So, what they do, they have combined precision and recall to give F1 measure, which is 2 into PR divided by P plus R, which is the harmonic mean of 2 numbers, and if it is too large, both P and R must also be large. So, another one which is called as receive operating characteristic or ROC curve is also used for this, and you have true positive rate which is given as TP by TP plus Fn. TP you remember is the true positive divided by the true positive plus false negative, and then you have the false positive rate which is the false positive divided by the true negative plus the false positive. So, this is defined as the receive operating characteristic. And then you have sensitivity and specificity, again defined in terms of sensitivity is nothing but TPR, which is the true positive rate, and specificity is the true negative rate, which is defined as true negative rate is Tn plus, that is the true negative divided by the true negative plus the false positive, and this FPR is nothing but 1 minus specificity. So, these are some of the measures that we use. So, we have explained and differentiated lazy and easy classification learning methods. We have only discussed the basics of nearest neighbor methods and analyzed them. We have not gone into a special algorithm or anything, we just in general define nearest neighbors. This is actually a lazy learning method. Okay, we have not looked at any eager learning classification methods. And then we looked at evaluation methods and evaluation measures. Again, some of the evaluation measures are specific to eager learning methods. There are other general also. We looked at both in this particular module. Thank you.